A standard fair cubical die is to be rolled 5 times, and the number of 6s obtained is to be noted. Calculate the probability of each possible outcome, and hence deduce that the binomial distribution is linked to the binomial theorem. So here, if we had a random variable x, it would follow a binomial with 5 trials and a probability of success of 1/6. Now, x could take the values here, 0, 1, this should be small x, 2, 3, 4, or 5. All of those are possibles. We could get no 6s, 1/6, all the way up to 5 6s. So let's look at the probability of x being 0. That would just simply mean that we got not 6 5 times. So that would be 5/6 to the power 5. Think about the probability of x being 1. That would mean that we got a non-6 4 times. And we also got 1/6. But we have to take into account here that we could have got a 6 on the first go, and then not a 6, not a 6, not a 6, not a 6. Or we could have got not a 6, 6, not a 6, not a 6, not a 6, and so on. Non, non, 6, non, non. And you can see there's 5 ways that we could do that. So we multiply there by 5. Now, let's just clear this up. And then look at the probability of x being 2. So we would get a non-6 3 times, and we'd get a 6 twice. Now, think of the ways we could do that. We could start off with 2 6s and then get not 6s. Or we could get 6, not, 6, not, and so on. If you think about this, there are 5 choose 2 ways of arranging those 6s. So here we multiply by 5 choose 2. 5 choose 2, if you calculate it, is 10. Now the others are symmetrical to those. So for 3, we're going to get 5/6 squared times 1/6 cubed. And clearly that's going to be multiplied by 10 because it's this situation, but just with one of the nots replaced with a 6. Probability x is 4 is going to be just 5/6 and multiply that by 1/6 to the 4. Clearly that situation is the same situation as we have here, except that we have more 6s and just a single n, but clearly there's 5 ways of arranging that. And then for x to be equal to 5, that means that we don't get any non-6s, and so we get 5 6s. And of course we could calculate all of those, stick them in the calculator and actually get numbers for them, but I don't think we really need to make our point. If you now consider doing 5/6 plus 1/6 to the power 5 using the binomial, what do we get? We get 5/6 to the power 5, and we'd be using the 1, 5, 10, 10, 5, 1 line of Pascal's triangle for the coefficient. So the next one would be 5, 5/6 to the 4, 1/6, and then the next one would be 10, 5/6 cubed, 1/6 squared. And then we'd have 10, 5/6 squared, 1/6 cubed, 5 lots of 5/6, 1/6 to the 4, and then 1/6 to the power 5. So at the bottom here, we have the binomial expansion, and the terms of that are the probabilities that we calculated up here. And so the binomial distribution is related to the binomial expansion.